This video proves there is no quantum eraser. A famous study by Yun-Ho Kim et al. Demonstrates that if you believe that waves and particles go in the same direction, then you are forced to accept the ridiculous idea that data can be erased backwards in time. We claim the conclusion is obvious, that waves and particles therefore cannot go in the same direction. We will analyze this experiment from the viewpoint of the theory of elementary waves, in which particles follow waves backwards, and we will demonstrate there is no quantum eraser problem. Yun-Ho Kim et al. Built a complicated apparatus which I'm going to simplify in this video in order to focus on the basic issues. Photons come from a laser on the left, go through a double-slit barrier, and then behind the double-slit barrier, a BBO crystal which divides each photon into two identical photons. So you end up with 4 photons, 2 of which represent the going through the upper slit and 2 of which through the lower slit. Photons 1 and 2 go up here to the target screen where they inscribe an interference fringe pattern, a wave pattern. Photon 4 goes down to a beam splitter, which randomly assigns it either to detector D3, which does know, or to detector D2, which does not know which slit was used. So in the final data set, it turns out that if you don't know which slit was used, then the interference fringe pattern on the target screen is still visible. But if you do know which slit was used after the fact, then the information on the target screen is erased, apparently backwards in time. This causes a lot of people to have migraine headaches. But there is an alternative, which is to look at the experiment with different starting assumptions. They believe that wave function collapse occurs at the detectors. We claim there are elementary waves of zero energy going from the detectors to the laser, and that wave function collapse occurs at the laser when a photon is emitted, and as it is emitted it chooses at random which elementary wave to follow backwards. From then on, it is a deterministic experiment. We start with the elementary waves starting at the detectors and going backwards through the equipment, backwards through the BBO crystal, backwards through the double slit barrier, and impinging on the laser. All wave interference is located at the laser. All decisions in this experiment are made by the photon before it leaves the laser. So this target screen, what does it mean? Well, if it has a wave pattern on the target screen, that means that there is wave interference at the laser. If there is no wave pattern on the target screen, that means there is no wave interference at the laser. So how could that be? Well, if at the laser you have elementary waves coming through both slits, those 2 waves through the bottom and top slit will interfere with each other, and you will get an interference fringe pattern on the target screen. If, on the other hand, you have no elementary wave coming through the top slit and only an elementary wave coming through the bottom slit, there can be no interference with only one wave, and therefore the target screen will show no wave interference. There are 2 kinds of elementary waves impinging on the laser, and the photon has to choose which one. It makes that choice at random. On the one hand, there's an elementary wave coming from the target screen and from a detector that does not know which slit the photon came through. And it turns out that when you trace that backwards, the elementary waves impinging on the laser will be using both slits. Because the waves use both slits, therefore they interfere with one another. There's either constructive intermediate or destructive interference of the 2 waves as they impinge on the laser. And because of that interference, there will be an interference pattern on the target screen. The other possibility for the photon to choose is an elementary wave coming from the target screen and from detector D3. Detector D3 can see the lower slit, but it can't see the upper slit because of the way the equipment is constructed. Now I've color-coded these waves so that anything connected to the lower slit is color-coded blue and anything connected to the upper slit is red. So when the BBO crystal tries to manufacture a elementary wave to go through the lower slit, it can do so because it has the ingredients it needs, which is a blue wave from above and a blue wave from below. But when the BBO crystal tries to manufacture a red wave to go through the upper slit, it cannot do so because it's missing half of the ingredients. Namely, there's no red wave coming from detector D3. So therefore the BBO crystal is unable to manufacture a red wave to go through the upper slit and impinge on the laser. Therefore there's only one wave, the blue one, going from the double slit to the laser, and you cannot have wave interference with only one wave. So therefore there's no wave interference if detector D3 is involved, and therefore there is a blank target screen. When we look at the experiment from this angle, there is no backwards in time destruction of data. Everything looks sensible and exactly what you would expect. Now, you might say, I like your idea of getting rid of quantum weirdness, but this idea of detectors sending zero energy waves in the wrong direction is totally weird. It does not correspond with my idea of nature. Well, there's a couple of things to be said. First, with TEW, we make our weird assumptions at the beginning. We say, yes, there are elementary waves with zero energy going in what you might consider to be the wrong direction, the direction opposite the particles. That's weird. But we pay our weirdness tax up front. Quantum mechanics, on the other hand, makes sensible starting assumptions and does not pay a weirdness tax and is therefore penalized by the taxing authority forever with a misperception that the quantum world is weird. For example, they say that in the quantum world, data can be erased backwards in time, which illustrates that the quantum world is viewed as completely weird, which is a symptom of the fact that they did not pay their weirdness tax, and are therefore misperceiving the quantum world as if it were weird, which it is not. I propose that it is better and more honest to pay your weirdness tax up front. And as far as what nature is really like, do you think you know what nature is really like? If the quantum experts knew for sure what nature is really like, then you would not find quantum mechanics experts saying, as they do, that there is a consensus that we don't understand the quantum world properly. Thank you very much for your attention.